So, hello everyone, welcome to this Quantum Club. In fact, it is the last one of the year. It's been a really nice series of talks and we're very grateful to all the speakers. I think that each talk was really successful. We're also grateful to you, the audience, for your enthusiasm and interest in quantum physics. And I hope you're ready for next year because we're preparing some other talks and also some new formats. And if during the summer you miss us, you can remember about our YouTube channel where you can see again all the talks from this year. So to close this series, we have an amazing guest, Gilles Brassard. So you of course know him as one of the inventors of quantum teleportation and also the author together with Charles Bennett of the first ever quantum cryptography algorithm that was published in 1984. He is professor at University of Montreal in the Department of Informatics, and his main interests are in quantum informatics, of course, and cryptography. And currently he is visiting professor at ETH. So one of his other interests is the interpretations of quantum mechanics, and this will be the topic of today's talk. Please welcome Gilles Brassard.
Merci, Alexandra. All right, so title of my talk, which I changed recently, only the title actually. Okay. So, were you told that our world is not local? It's a question, but I don't need to answer because I know the answer is yes. Because, well, at least those of you who were at Nicolas Brunner's talk on quantum nonlocality. And I'm going to start just reminding you of what he told you, because it was about half a year ago. Just to set the stage, I'm going to use his slides at the beginning, so that you will be in known territory if you were there or not. It doesn't matter because. All right. So the answer is were you told our world is non-local? The answer is yes. That's what he said. And the purpose of my talk is to tell you that that's not the case. All right. You probably also went to another quantum club about a month later. And I haven't had time to listen to it, so I'm not sure what they said, but knowing Nicolas Gisin, he certainly believes that the world is not local. So he would also say, yes, the world is not local. He would be pretty sure of that. Renato Renner is not so clear, and Jörg, I don't know. But let's go back to Nicolas Brunner's talk. Again, I'm going to start by giving you a refresher of what he said, what he told you. All right. So again, these are slides that I copied directly from his talk without permission. But all right. Sorry, didn't have time to ask. So here's a question that he asked at the beginning of his talk, his quantum club. He asked the following question. Well, let's say that we want to see if quantum theory can be understood in a sort of classical setting. And it's much more interesting to do that not by lining up equations, but by playing games. And in particular, let's imagine that you have a device that belongs to Alice, and this device has an input-output. You can input some parameter, you get some output from the device, and you don't need to know any quantum mechanics. You don't need to know what's inside the box. It's sort of a black box, actually. All you're going to do is to look at the input-output behavior and see if you can understand that in classical terms. Well, there's going to be quantum stuff in the box, but again, you don't need to know that. It's only a question of looking at the input-output, and could you explain that classically? That's the game. And if you have a single device, then essentially the only thing that you can do as an experimenter, if you just play with the device, you can build a sort of a probability distribution of, so you play with it, you put various inputs, look at the outputs, you see that it's not deterministic, the same input could give different outputs from time to time. So what you can do is to build sort of a table of probabilities. Of course, you're going to observe frequencies, which you interpret as probabilities. As a function of the input x, what's the probability that you get the output a? And you work for a while with this box, and you ask yourself, can you explain it classically? And the answer is yes. Because if you have a single box that in fact is quantum, there's nothing that this box can give you that you could not get classically. At least with enough computing time classically. And without assuming some computational complexity stuff like factoring takes a long time, without any assumption about things we don't know how to prove, then you just cannot prove when you look at the output of that box that something non-classical is coming out. And the trick to get something really interesting and to play that game really goes back to, again, this is Nicola's slides. So the question is, you want to get something that you could not explain classically. And the challenge is how to prove that that what you observe is incompatible with a classical device. That's what I just told you. Well, again, with a single device, you cannot do that. But John Bell was an Irish physicist working at CERN, so very near here in Geneva. So John Bell, this picture is taken in 1982 in his office at CERN. And this is not Bell's inequality. It's not his Bell inequality. But in 1964, he wrote a breakthrough paper about which Nonlocal Brassard told you in his club. And the idea was that if you have not one but two devices, and if they are far enough that they cannot communicate, if you're able to choose your inputs on each device and see the output, and do that with enough simultaneity that neither device can tell the other what its input is. So that the output of a device can depend only on its own input, but not on the input of the other device. So if you're able to do that, so you need the devices to be far enough and to be sufficiently precise with timing, but if you can do that, then quantum theory predicts things that start looking strange. Again, as Nonlocal Brassard told you about. Specifically, so now we have two devices. We have a source in the middle that is allowed to distribute programs to these two devices. Something we call a local hidden variable. You know, the lambda here. So each time you press the button, this source chooses a lambda randomly somehow and sends it to both sides of to both devices. And now each device, when you push the button, will have to choose the outcome as a function of which input you set in and of lambda, the current lambda. And from time to time, lambda will be different, but each time the output of Alice should depend only on its input and lambda, not on both inputs, and vice versa. So that's a game that Bell studied in his 1964 paper. And in particular, so this is not at all from Bell's paper. This was discovered 5 years later, in 1969, by Glaser, Horn, Shimony, and Holt. But we usually talk about it as if it were Bell's inequality. It's not. Bell's inequality was much, much more complicated than this. Integrals and all sorts of things. But when people talk about Bell's inequality, they usually mean this, 1969, not 64, and not Bell. But nevertheless, Bell was really the first person to think about these things, or to solve it, I should say. So again, the game that Nonlocal Brassard explained to you is the following. There are only two possible inputs for Alice and Bob. Let's call them X and Y, 0 or 1. And only two outputs, which Nonlocal called +1 and -1. And the rule of the game is that if X and Y are 0, or if at least one of x or y is 0. So all cases except when they're both equal to 1, then the two boxes must give the same answer. But when the answer, when the input is 1, 1, when you ask 1 to both boxes, then they should give opposite answers. And I'm not going to repeat what Nicolas told you. I mean, I'm not going to prove it to you the way he did, but it's not very hard to prove that it's not possible to win all the time. No matter how you choose lambda, if the outcome depends only on the input on one side and lambda, then no matter how lambda is chosen, you will always fail at it in at least one of the 4 possible questions. There are 4 possible questions, 0, 0, 0, 1, 1, 0, 1, 1. 4 possible pair of questions, and you will always fail at least one of the 4, and therefore, the score of a classical player cannot be better than 3, 4. You win 3 times out of 4 at best. Whereas, and that's a Bell inequality. It's not Bell's original equality, but we call it the Bell inequality. That no matter how you do, the score will not be better than 3/4. But if you go quantum, and again, I'm not going to repeat how this works, as Nicolas told you, but if you go quantum, and if the two sides can be entangled, then well, in Nicolas' slide, you have this strange formula which doesn't quite match with the score we were talking about before. But if you transform it back into the score, what it says that quantumly, you can have a score of cosine square pi over 8, which is about 85%. So that you violate Bell's inequality. Entanglement will allow you to win this game with probably 85%. And it's easy to show that classically, no matter how you set up these local variables, this lambda, no matter how you just choose the programs for Alice and Bob as a function of lambda in their inputs, you will never win more than 3 times out of 4. And because 85% is bigger, something strange is going on. So the idea is that without knowing any quantum theory, all you have to do is to build these boxes, put them far enough, play with them. Alice and Bob will play with the boxes, and they will collect statistics, and their statistics will show that they win the game more than 3 times out of 4. And therefore, these boxes are not classical. That's the idea. Very good. So Bell's theorem, again, this is taken from Nicolas Bennet's talk. Bell's theorem says that there are some quantum correlations, such as those I just told you about, that cannot be explained by any local theory. And we call that quantum nonlocality. And again, quantum theory tells you that this should happen, and then you can actually do it in the lab, and indeed it happens. So it's not only, if you could not verify experimentally this behavior, it could either be that quantum theory is not classical, or that it's wrong, and that these predictions that quantum theory give you will not happen in real life. So you really need to do the experiment to decide. But indeed, this can be done experimentally, and I think it's the last slide from Nicolas that I copied for you. The most famous experiment that verified that that violated Bell's inequality in 1982 was Alain Aspect. And then Nicolas Bennett said this, which is really very funny. So here's a picture of Alain Aspect in 1982. And then Nicolas said, the only thing that didn't change is a mustache. Because of course he doesn't look like this anymore, but he still has a mustache. And indeed, when he got a Nobel Prize last year, 2022 actually, this is sort of a Nobel Prize picture. Oh, okay. So, same mustache. and I cannot resist showing you what he looked like 9 years ago. Because we were together at the Royal Society where he was admitted as a foreign fellow, a foreign member of the Royal Society. And I'm there because I was his nominator. I'm very proud of of this success at the Royal Society, although it was not, I would have been rather shocked if he hadn't made it, but he did it. He got it on first try. Very good. All right. A couple of weeks ago, Alain Aspect gave a talk in Zurich. A really, really great talk. It's a sort of a popular science talk. And so I see his little mustache. But the point is that his conclusion from his talk, or the whole point of his talk, was again the same thing, which is that local realism must be abandoned. And he wrote a paper a few years ago, closing the door on Einstein Bohr's debate. Again, we should renounce local realism. And again, so he got a Nobel Prize. He got a Nobel Prize in 2022, exactly 40 years, almost the day, 40 years after his landmark experiment in 1982. Although he was not the first, before him, John Clauser did the first conclusive experiment that violated Bell's inequalities. You may remember I told you before that the Bell inequality that we're talking about is not Bell's 1964, but CHSH. And the C of CHSH is Clauser. So he because Bell's, if you look at Bell, if you read Bell's paper, it's a masterpiece. But if you read Bell's paper, you have no idea how he could possibly test that. And Clauser was really ticked by that, and he figured out with Horn, Shimoni, and Holt, he figured out an experimental test that would be conceivable. He could actually do it, and he did it. And he got a Nobel Prize for that. Exactly 50 years, half a century after. His experiment was 1972. And exactly half a century later, he got a Nobel Prize for it. But he never got a position, a professor position, because this experiment ruined his career. He was considered sort of a crackpot. After he succeeded, the general advice to him was, very nice, now start doing some real physics. And really, he never got a professor position after that. Whereas Alain Aspect, before embarking on his experiment, he went to see Bell, and he asked Bell for advice. Do you think that I should do this experiment? And Bell asked him, do you have a permanent position? And Aspect said yes. So Bell said, all right, go ahead. He knew about Clauser. He didn't know about that. He knew that Clauser yet didn't have a position. He didn't know that 50 years later he would still not have one. But well. And of course, Anton Zeilinger in Vienna shared the Nobel Prize. So this, and moreover, their Nobel Prize is exactly 100 years after Einstein's. Sort of remarkable. So Nobel Prize is 50 years after the first experiment, and another 50 years before, Einstein got a Nobel Prize. And by the way, Einstein got a Nobel Prize for quantum mechanics, not for relativity. Now, if you are really, if you're really knowledgeable about history of Nobel history, you say, no, Einstein got a 1921 Nobel Prize, not 1922. So it's not 100 years before. It's 101 year before. Well, yeah, but no, because Einstein got a 1921 Nobel Prize, but he got it in 1922. Because in 1921, the Nobel Committee was unable to decide whom to give the Nobel Prize to in physics. So there was no Nobel Prize in physics given in 1921. They sort of wanted to give it to Einstein, but they weren't so sure. So they decided to skip it. And in 22, they gave two Nobel Prizes. They gave an official 1921 Nobel Prize to Einstein, and the 1922 Nobel Prize to none else than Niels Bohr. So it's really remarkable. All right. So they got a Nobel Prize for what? For experiments with integral photons, establishing the violation of Bell's inequalities. In other words, it's their experiment, in addition to Bell's theorem or CHSH theorem, that sort of established the non-locality of our world, they think. And indeed, after a Nobel Prize was awarded, you could see all over the press statements of the sort that Einstein was wrong, that the universe is not locally real, contrary to what Einstein believed. The Physics Nobel Prize proved it. And that what local means, that objects can only be influenced by their surroundings, and any influence cannot travel faster than light. And so here's, again, that's in Scientific American, but everywhere else, there's evidence, the Nobel Prize laureates gave evidence that show that objects are not influenced solely by the surroundings. Said otherwise, there's what Einstein derisively calls spooky act at a distance is real. And again, so there were all these press clippings saying how much Einstein was wrong, and that was proved by the Nobel laureates. Well, sorry, Einstein was right. But let's continue. So does Bell's theorem imply that our world is not local realistic? Of course not, because Bell's theorem is mathematics. You also need the experiments. So do Bell's theorem plus the experimental vindication of the 2022 Nobel Prize winners, do they imply that our world is indeed local, not local realistic? And the point of this talk is to convince you that the answer is no. It does not imply that in the least. Very well. It's not new. Already in last century, Deutsch and Hayden, and Deutsch, by the way, is really one of the most important fathers of quantum computing. Deutsch and Hayden in 1999, published in 2000, wrote this amazing paper. So this was very last century, that all information in quantum systems is, notwithstanding Bell's theorem, localized. Said otherwise, measuring or otherwise interacting with a quantum system somewhere has no effect on the distance system. No effect at the distance, no spooky action, period. And so in that paper, in this paper, they give a complete explanation of how quantum theory works in a local universe, how you can violate Bell's inequalities without having to resort to any non-locality whatsoever. That paper didn't really, was not noticed very well. Not so many people noticed that paper. I didn't at the time. I did later, but when it came out, and there was maybe one reason is that it's very hard to understand. Good luck. If you want to read that paper, good luck. Nevertheless, the abstract is short, clear, and crisp. Now, when you plunge in it, what it's talking about, it's very hard to understand. But that's okay, because one of my former students, Charles Bennett, deciphered it for you. So instead of reading Deutsch Hayden, read the ABC of Deutsch Hayden descriptors in quantum reports, and you will know all there is to know about it. It's very simple. Once it's explained in simple terms, it's simple. Well, it remains not that simple, but still, at least understandable. And Deutsch Hayden not only explain how to do all quantum effects, everything they explain how to do it without needing any extra distance, without needing any non-locality. There's no need for non-locality to do quantum theory. But in particular, they explain how to do quantum teleportation. So in Deutsch Hayden, if you're brave enough to read it, you will know how to understand quantum teleportation in completely local terms. Now, if you don't know quantum teleportation, it's here on my back. And this simple circuit explains how to do quantum teleportation. When you look at it, you could not tell that it's local, but that's okay. And in fact, after Alain Aspect gave his talk, of course I was there at Alain Aspect's talk a couple of weeks ago in Zurich, and I was wearing the same T-shirt. and someone took a picture. So this is me, of course, at the reception, the reception after Alain Aspect's talk. So you see at the top, it's Andreas Wallraff that took the picture. Or maybe, I don't know if he took the picture, but he recently seen in the halls of ETH Zurich. Do you recognize the quantum circuit teleportation? Who might be wearing such a t-shirt? Question mark. Of course he knew it was me. And I'm very proud of, look, I don't think that I've ever been seen more than 14.8 thousand times. I'm sorry, 18.4 thousand times that this picture has been seen. So now I'm famous. But good news again. The same Charles Bennett also deciphered how to do teleportation for you. So if you read this instead of Deutsche, then you will understand quite quickly how to teleport in a local universe, which seems totally impossible if you know what teleportation is about. But yet you can. All right. So the usual argument against local realism is the following. Number one, quantum theory cannot be described by local hidden variables. The lambda I had before, or lambda that Nikola Brunner had. Two, any local realistic world must be described by local hidden variables. And therefore, even Aristotle would have been able to conclude that quantum theory cannot be local realistic. This is a correct conclusion from those two statements. By the way, it's not a modus ponens, it's a modus tollens, but that's okay. Well, one is true, that's Bell's theorem. This is true. So basically, this is what Bell proved in 1964, and this is what Nikola Brunner told you in his club 6 months ago. And you guessed it, number two is false. And that's the point of this talk. And since number two is false, well, the conclusion does not follow. My wish in this talk is to convince you without any possible doubt that the point number two is false. Notice that two being false does not imply that quantum theory can be local realistic. It only implies that you cannot conclude it's not local realistic from these experiments. That quantum theory can be local realistic was proven by Deutsch and Hayden, but that's much more complicated. And I'm not going to do that in this talk. And not even the easier version of Charles Bennett. I'm going to, so you will not, at the end of my talk, you will not know how to do quantum theory local realistically. But you will know, and you will understand, that just from a mere violation of Bell's inequality experimentally in our world, just from that, you cannot conclude that our world is not local realistic. And I'm going to do that by showing you a fantasy world that is local realistic and violates Bell's inequalities even more than quantum theory. And it's very simple. That's the point. Again, then you have to work out. So this raises an alarm that, well, maybe after all, the world is not, maybe the world is local. But it doesn't prove it. Again, I repeat this, I just want to make sure you understand. What it does prove is that you cannot conclude that the world is not local realistic merely from a violation of Bell's inequality, experimentally speaking. All right. This is based on a paper that I wrote with my former student, Paul Raymond Robichaud, who did all the work. It's entirely his ideas. I'm just a messenger. So my purpose is to tell you what Paul's idea was, because it's so beautiful and simple. And I wish to stress the order of authors is alphabetic, as is the case usually in theoretical computer science. And it all fits in one poster. So I'm going to go through this poster bit by bit with you now. First, let me describe the imaginary world in question. And I want to stress, this is an imaginary world. meaning that it's not meant to be the real world. It's not the real world. It can, in that imaginary world, you can do things that you could not do in our world. So it's not, the purpose is not to describe our world. It's totally imaginary, but it's locally realistic, and it violates Bell's inequalities. That's the point. So because it's not the real world, I'm free to set the rules any way I want. You don't have to ask, you cannot ask me, how is that possible? It's not possible. The point is that it's local and realistic, and it violates Bell's inequality. So, and this imaginary world is, so these slides, I had two students of Stefan Wolf, who is a professor in Lugano, but who was giving a talk, who was giving a course at ETH Zurich. And two students in that class gave a presentation about this work, and I borrowed their slides with permission. The drawings, the poster was made by Louis Ferdinand Leclerc, according to Paul Raymond-Robichaud's instructions. All right, I wish to say that some similar ideas were already in Colin Bruce's book called Schrodinger's Rabbits, which we didn't know about it when Paul discovered this, what I'm going to tell you now, 10 years ago. When Paul discovered that and came to my office, and I was flabbergasted. My world was shattered in 5 minutes when he told me this idea he had. Just the day after, I had taught in class, as always, that quantum theory is not local realistic because you can win this Bell game, the game I showed you before, more than 3 times out of 4, and therefore the world is not local realistic. And I've been teaching that for years and years, and then Paul came to me the next day. Nope. All right, so we've seen this already. So I'm just recopying Nicolas Brunet's slide because this is the game we're going to play. So just to remind you, this game, there are 2 inputs, 0 and 1 on each side, 2 possible outputs, plus and minus 1 on each side. And the rule of the game is that you should give the same output in all cases except when the input is 1, 1. That's the only case where you should give opposite outputs. And just to remind you, with local invariants, you cannot win more than 3 times out of 4. Whereas quantum wins 85% of the time. Very well. Now I'm going to show you how to win 100% of the time. But by the way, there's a theorem due to Thorelson that this is the best quantum can do. The best classical can do is 3 times out of 4. That's very easy to show. The best quantum can do is 85%. That's a lot harder to show, but it's a theorem. I'm going to show you how to do it, to win all the time at that game. Again, it's a fantasy world. Okay, so here's how you do that. Let me first describe the imaginary world in question. You have two characters, Alice and Bob. And they are given these boxes. So these boxes really correspond to those boxes, right? So Alice and Bob are given these boxes, and they are in spaceships. With them in spaceships, they will be far enough, because it must be that they cannot communicate while they do the experiment. Otherwise, it's just very easy to cheat. You have to be far away. So let's put them in spaceships. And this, in fact, these boxes were invented in theory by Popescu and Roglic in 1994. Here's how it works. When Alice, this is Alice's box, and she's going to push a button. The box, they have 0 and 1 button. They're the same as a 0 and 1 that we had in Nicolas' talk. But instead of +1, -1 as output, it will be flashing a red or blue. More fun. Or red or blue, I don't remember. Anyways, so let's say Alice pushes button 1, and then her box could turn either red or green. As soon as she pushes the button, the box flashes a color, which is either red or green. And it's half and half. And Bob also will do the same. So Alice and Bob, they will both choose at random to push 0 or 1, and the box will flash a color, red or green. And the magic rule is that if they both push 0, then they must see the same color. If one pushes 0, the other pushes 1, they must also see the same color. And if they both push 1, they must see different colors. Exactly the rule that we had before. So we know that this game cannot be won more than 3 times out of 4 in a classical world ruled by local variables, these lambdas, and that it can be won about 85% of the time with quantum. Now in this fantasy world, in fact, we can win all the time. And I'll show you how to do that. Quote, sort of how to do that. So to summarize, these boxes come in pair, and by the way, they are one-time use boxes. When you push a button, it flashes green or red, and then it's finished. If you want to repeat the experiment, you need a whole lot of pairs of boxes. So when you push a button, it's half the time red, half the time green. And the magic rule, again, is this one. Okay. Now Alice and Bob go on their spaceships with their load of boxes, of pairs of boxes, one for Alice, one for Bob, for each pair. And they play with it. And Alice, for instance, Alice will flip a coin, and Bob flips a coin, so Alice flipped 1 and Bob flips 0, for instance. And then Alice pushes the button 1, because she flipped 1, right? So she will push button 1. And as we've seen, and let's say that her box flashes green. What does Alice know? If Alice believes that the boxes work properly, what can she infer from the fact that she saw green? Well, she knows that what she knows is that if Bob pushes 0, then he must see green as well, because she pushed 1. If Bob pushes 0, 1 and 0 is a case where they should see the same color. So by seeing green, by pushing 1 and seeing green, Alice knows that if Bob pushes 0, he will see green as well. She also knows that if he pushes 1, Bob will see red, because that would be a case 1-1, and then put 1-1, they should see different colors. So if Alice pushes 1 and sees green, she knows that if Bob pushes 0, he sees green, if Bob pushes 1, he sees red. In other words, Alice, by using the box, knows knows the program, the totally deterministic program in Bob's box, but without having interacted with Bob's box in any way. So, and that's the gist of the EPR argument. I didn't mention EPR, sorry. EPR stands for Einstein, Podolsky, Rosen. In 1935, Einstein, Podolsky, and Rosen wrote a paper that changed the world. They introduced entanglement, and I don't have time to really tell you more about the history of this paper. It's really interesting, but today, and it's been the case for at least a decade, this is Einstein's most cited paper, by far. It's even more cited than teleportation. All right, and so the argument in the EPR paper was that, if you translate it to these boxes, would say that Bob's box, it has to be predetermined, because Alice can know how Bob's box will react to both buttons. Alice can know what Bob's box will give without touching it, only by touching her box. And therefore, because they are arbitrarily far apart and there is no spooky action, thought Einstein correctly, therefore, Bob's box has to be predetermined. That's the whole point of the EPR. So now they go out in space and they try it, and they try it again, and they try it again, and they try it again. And no matter how many times they try it, it works. Their boxes follow the magic rule all the time. Again, it's a fantasy world. We cannot have that in our world. Now, okay. What about our world? Well, in our world, we have to be content to think about imperfect nonlocal boxes. Remember, if it's classical nonlocal box, it will be imperfect and work 3 times out of 4. If it's quantum, at best, it will work 85% of the time. So in general, let's say that an imperfect pair of nonlocal box will follow the magic rule, probability P, and this will be the rule of probability 1 minus P. And according to classical physics, best possible is P is 75% when you use local variables and no communication. If you communicate, you can cheat completely. So that's why you far apart. But quantum theory allows you to win 85% of the time, and no better. And therefore, quantum theory is non-local. That's the usual argument. Not so fast. Now I'm going to show you, so again, the usual conclusion is that a world like ours that contains non-local boxes that work more than 5% of the time, such a world cannot be both local and realistic. And so our world is like that, because 85% is bigger than 75%. All right. I'm now finally going to tell you how you can actually win 100% of the time and be local realistic in a fantasy world. That's what Paul called parallel lives. I think it's a very nice, he coined a really nice term, parallel lives. If you're familiar, by the way, with many worlds interpretation of Everett, it's different. That's why we have a different name. And I'll tell you how it's different as we go along. It is similar, but different. All right, here are Alice and Bob in their spaceships. And now let's say that they're far apart. Let's see what happens if Alice pushes, say, button 1. Well, from all I've told you already, you will say, oh, with only 1/2 she sees green, and 1/2 she sees red. No. In the fantasy world, that's not what happens. In the fantasy world, Alice splits. With the box, Alice, the spaceship, split. So now we have think of in 2 bubbles. There's one Alice is green, one Alice is red. And these 2 Alices, they live in the same place, but in parallel, hence parallel lives. However, if you're familiar with many worlds, Everett's many world, it's not the whole universe that splits, which can hardly be more non-local than thinking the whole universe splits in an instant. It's only Alice. Alice splits. There's one green Alice, one red Alice, and nothing at all happens at Bob's. No action at distance. Now, all right, these 2 Alices will not interact ever. They're not even aware that there's another Alice. Each one of them sees one color and one color only, and has no idea that there's another Alice who saw the other color. It's right there, but no access to it. Very well. And now, this split ripples through space at the speed of light, but no faster. So there's no effect, nothing happens faster than light in this theory. And I said it already, but most importantly, Alice is pushing the button and Alice splitting has no effect on Bob whatsoever. But what about Bob? Bob, see, no change. Now let's say that Bob pushes button 0. Now Bob pushes 0, you guessed it, splits. So now we have 2 Alices and 2 Bobs. In a sense, it's like 4 universes, but again, it's really 2 these two Alices are totally independent from those two Bobs. And now, they're all independent, and now let's say that Alice and Bob, Alice pushed 0, I pushed 1, Bob pushed 0, Alice saw both colors, Bob saw both colors, but they don't know that. Each think that there's only one color. And now they decide to compare the data. So they ignition, right? And now they rush to meet each other. And that's when the magic happens. At the moment that they meet, because Alice pushed 1 and Bob pushed 0, they should see the same color. And when they meet, green Alice will only see green Bob, and red Alice will only see red Bob. And that's it. Of course, you can have all 4 combinations. If you both push 1, then green Alice will see red Bob, and red Alice will see green Bob. So all 4 can happen, and they all work according to the magic rule. So you see, there was no action at distance at all. It was totally local. Again, it's a fantasy world, but it was totally local actions that happened. And in particular, when they meet to their amazement, verify that the boxes worked 100% of the time. So when they meet, and only when they meet, will they be able to verify that they get different color if and only if they both push button 1, which is impossible. And the crucial thing to understand, if you think in terms of violating Bell's inequalities, when you have these experiments, now I'm going back to real life, to our world, to quantum world. If Alice and Bob do Bell inequality violation experiments, and Alice and Bob, they share entanglement. They no longer share these boxes. They actually share real, honest quantum entanglement. And Alice, on her side, she does all these experiments. She chooses at random which measurements to make on her side, how to set the knob, if you wish, on the box. And she records, she chooses at random which setting of the knob, and she records the answer. And Alice builds a table. Alice builds a table of input-output. And far apart, far away, Bob does the same. Bob also builds a table of input-outputs, result of his experiments. Well, if you look at either one of these tables in isolation, there's nothing special, nothing mysterious. They're just totally random outputs, uncorrelated to anything. The output that Alice sees is random 50-50. Again, I'm talking about the real world now, quantum. So the outputs that Alice gets is totally random, 50-50, uncorrelated not only to what Bob did on his side far away, but even in Alice's setting. It's just nothing special about unless you don't believe in randomness, then you're amazed that there's randomness. But except for that, nothing special on Alice's table. Nothing special in Bob's table. Bell's inequality is not violated when Alice and Bob make their measurements. Bell's inequality is violated when the measurements are brought together. It's the joint measurements that is special, that violates Bell's inequality. It's neither Alice's measurement nor Bob's measurement. It's only when the measurements are put together, when Alice and Bob, they build these tables, it's only when these two tables are brought together that you see, oh, Bell's inequality is violated, how amazing. And the whole point is, bringing the data together cannot be done faster than light. So that in the end, Bell's inequality is violated, yes, but no faster than light, and there's no mystery anymore. Of course, to believe that, you have to believe that the result of the measurement never becomes definite. Because if when Alice measures, she gets an answer, which she records, and that answer that's the one and only result of her measurement, and same thing for Bob, then it's not because bring the data together that it was going to change. So if Bell's inequality is violated in the middle, it was violated already. But if you believe, which is hard to swallow, but if you believe that there is not a single outcome to the measurement, then mystery vanishes and you can do it. Here I explain you how to do it with this in this fantasy world. And if you want to do quantum theory, it's not going to be, it's more difficult. You have to, like I say, obtain the correct, win the game 85% of the time, not 100%. Sort of funny, 100% is much easier. To win 85%, you have to work harder in your head, in the theory. But it can be done. And not only can you build or explain how the actual violation of Bell's inequalities that we see experimentally in a local realistic manner, again, by working harder than what I told you. Not only can you do that, but again, Deutsch and Hayden discovered how to do the whole quantum theory, not just one example of Bell violation, including teleportation. All right. So the key idea is that in this imaginary world, the EPR argument, which I showed you before, the EPR argument was that because Alice, by pushing a button and seeing the outcome, she knows exactly how Bob's box will answer to both measurements that Bob can make. That was the EPR argument. Well, no, that's not what happens. The EPR argument does not hold. It's not because whenever Alice pushes a button, she can predict something about Bob. She cannot because she's here. Bob is far away. Alice, by doing something, has no effect on Bob. No, what she's predicting is not what's happening at Bob simultaneously, which would be non-local. What she can predict in how the various lines will interact in the future. That she can predict. But there is no non-locality about it. All right, so this proves that it's wrong to claim that any world that violates Bell's inequalities has to be non-local. Again, it doesn't prove that our world could be local realistic. That's harder, but it's been done. All right, so how about our world, meaning quantum theory? Well, again, Deutsch Hayden solved. Okay, my time is over. Let me just skip a bit and tell you about the main theorems that Paul proved. Here we go. So give me a few more minutes. I will tell you what Paul really did. He did what I told you already, but he did much more. When Paul discovered that we could explain the non-local boxes, we could win all the time with non-local boxes in a local realistic manner, we didn't know about Deutsch Hayden then. It was sort of disappointing to realize that, well, this is all known already. Although not for non-local boxes, only for quantum theory. But so then I told Paul, all right, explain quantum theory to me in the same terms that you've explained in the local boxes, and it took a few years, and he did it. Even though, again, Deutsch Hayden had done it before. But then I asked Paul, all right, now let's go further. The only thing that an experimental physicist can do is like push button and see outcomes. I'm not trying to play them down, of course, not at all. They're far from it. But what I'm saying is that the realm of an experimental physicist is to do experiments and see what's the outcome that happens probabilistically from the settings. Right? That's what they do. And then we have to collect all this data from experimental physicists and derive a theory. And that's what Newton did, for instance, based on, or Kepler, based on Tycho Brahe's observation, was able to find the laws of planetary motion, more or less. It had to be slightly fixed by Einstein, but more or less. But what I'm saying is that what the experimental physicists do is he makes experiments and he gives us the result of these experiments, and then it's for the theoretical physicist to try to figure out the rules that explain what's been observed. And that's what happened in the early days of quantum theory. There were all these experiments that we didn't quite know, and so the rules were derived in quantum theory, and these rules predicted some amazing things like entanglement, which then had to be verified experimentally. So it's a game that, like this, give and give. But all of that process is only not about explaining what's going on. It's about being able to predict the result of any subsequent experiment, including natural phenomena. So you derive these rules not to understand the world, but to be able to predict it. And Bohr was convinced that trying to explain physics is not science. It's wrong to try to explain how it's possible. You really should be content in deriving these rules of what you would observe. Now, the point I'm getting at is that the theory that experimental and theoretical physicists derive is what we should call a phenomenal theory. It's a theory about what can be observed in the world. It's not a theory about how the world really is, which is more the turf of philosophers. Now, philosophers can take the phenomenal world, a phenomenal description of the world, and try to derive an explanation that we call noumenal. That goes back to Plato. So the noumenal world would be the real world, which we can only imagine. We don't know we don't really know, but we can imagine. We can try to derive a real world from the phenomenal world. The phenomenal world being the only one that we can have access to. Now, in the phenomenal world of quantum theory, one very important thing is that it does not, at the phenomenal level, meaning what you can observe, quantum theory does not contradict special relativity. Despite appearance of non-locality in quantum theory, none of that can be used to signal information fascinatingly. So Alice, by doing something here in standard quantum theory, can have an effect at Bob's over there, but that effect is not observable. So in standard quantum theory is non-local, yes, but it's non-signaling. It cannot; these non-local effects cannot be used to signal from one place to another faster than light. So we can have, so the notion of non-signaling is a phenomenal notion. The notion of local realism is a noumenal notion. Quantum theory, we all agree, mostly, is non-signaling at a phenomenal level. And Paul proved these two theorems, and I will go over time just a little bit. So Paul proved these two theorems. One is that all local realistic theories are non-signaling. That's obvious. If when you do something here, it has no effect there, which is what local realistic means, well, then it has no observable effect either. It has no effect and there's no observable effect, which is what non-signaling is. So it's totally obvious that if you are local realistic, you are non-signaling. Now in mathematics, if you read a math paper, if you want to find an error in it, it's published. It's been published for years. And you just say, I'm going to pick at random a math paper and say, I want to find an error in that paper because the author is famous. Well, here's a recipe. Look everywhere he says it's obvious and find one of them that's false. Right, so this is obvious. All this to say you need a proof. Well, here's the proof. That's the only math I'm going to flash today. But the red part is the definition of local realistic. The blue part is the definition of non-signaling. So if you're local realistic, you're non-signaling. Forgive me for not going any further, deeper in this. But the point is that Paul proved the amazing theorem that all non-signaling theories are local realistic. What this means is that non-signaling theory, by definition, non-signaling is at a phenomenal level. So if we have a phenomenal description of, phenomenal theory of the world, our world or any other world, if we have any physics, if we have a phenomenal description of physics that's not signaling, then you can always lift it. That's the big theorem of Paul. That's really his achievement. From a phenomenal description of physics that is non-signaling, you can always lift it to a nominal level that's local realistic, and that is, right, that's local, right? So you can always go from a non-signaling theory, which is at a phenomenal level, and lift to a nominal theory that is local realistic. And so, well, there's a caveat. The phenomenal theory needs to obey reversible dynamics because this is done with group theory somehow. And the groups are reversible. That includes unitary quantum theory. And unitary here is important. Meaning if you believe in the collapse, if you believe that a measurement really has an outcome, a single outcome, due to this mysterious process known as the collapse of a wave function, which is totally outside quantum theory. There's nothing in quantum theory that is coherent with having a collapse. So it's like added as magic on top of quantum theory. Oh, now there's a collapse because it's not big enough. Complete nonsense. But if you believe in collapse, then the phenomenal world is no longer reversible, and this does not apply. But unitary quantum theory is reversible at the phenomenal level, and therefore it's local realistic. Now, doesn't Bell's theorem preclude this? No, Bell's theorem is about local invariables, not about local realism. So we need other ways to be local realistic, some other ways to be local realistic than local invariables. Again, to go back at the beginning of my talk, the points 1, 2, 3, 1 and 2 implies 3. 2 was that the only way to be local realistic is to be ruled by local invariables, which I proved is not true. So there are other ways to be local realistic. And there are 2 keys, and it's going to be quick because I told you already. One is that the test, so this is really what I told you, but now it's written. When you do tests of those inequalities, the test is not complete until you've compared the data. And the data cannot go faster than light. And for that to make sense, it has to be the case that the result, that measurements are not definite. If measurements become definite, this doesn't make sense. So we also have to believe that measurement outcomes never have to become fixed and definite. And by the way, Nicolas Gisin recently was at a conference at Les Diablerets, and Nicolas in his talk said that measurements have outcomes. So Nicolas Gisin this time believes that measurements have outcomes, therefore he believes that what I'm telling you about is complete nonsense. That's okay, we're good friends. Really. We agree to disagree, but that's okay. So he says a theory without measurement of models is not physics. Fine, I'm not doing physics. What do I care? I'm a computer scientist. All right, so just to finish, so you must admit that all possible results can occur simultaneously, and this, it does smell of Everett's many world, but it's really different. Again, in parallel lines, there is this, yes, I make a measurement and both outcomes occur in parallel, but with no effect elsewhere. It's not a whole universe that splits, it's really a local split. It's a very big difference, much more reasonable. And not only is it different from many worlds in that respect, but it's a third theorem that Paul proved, which is in any local realistic interpretation of quantum theory, the nominal state with the real state in the real world, the real state of the universe, it cannot be the quantum mechanical wave function. And Everettians, pure Everettians, believe that they solved it all because the state of the universe is a wave function, and that's it, and there's nothing more to say. Well, fine. If you don't care to be local, fine. But the theorem that if you take the wave function, the standard quantum mechanical wave function, if you take that as the state of the universe as a whole, well, then you cannot be local. And this is the title of the Einstein-Prost theorems in 1935 paper. Can quantum mechanical description of physical reality because they're complete? That's the question they pose in the title. And the answer is no. They were right, because they pose the question, but of course what they mean is no. The point of their paper is no, it's not complete. And they were right. The quantum mechanical description of physical reality is not complete under the metaphysical assumption of locality. And you need this assumption. If you don't care about locality, you could say, like Bohr, yes, it's complete. Fine. Like Nicola. And not only the answer is no, not only the answer is no, the quantum mechanical description, standard quantum mechanical description is not complete, but yes, it can be completed. That's what Deutschland did. You can take standard quantum theory, but take it only at the phenomenal level, and then you can complete it. That's what Einstein dreamt of. You can complete it to a complete local realistic theory that gives exactly the same predictions. You don't change anything about the phenomenal world. You don't change what you would expect to see at an experiment. You change none of that, but you give it an explanation that's local realistic. And that is a completion of quantum theory. That is what Einstein wanted in 1935. So I finish by citing Bell again. Either the wave function as given by Schrödinger's equation is not everything, or it is not right. Well, Bell was right about this. It's not everything. All right. You can read all the details in that paper. It's 62 pages long. It's 62 pages. But it's very, very easy to follow. It's really step by step. It's not like Deutschland. You can read it just before going to sleep. It's very entertaining. It's just theorem and lemma and theorems of mathematics, one after the other. But each step is very, very, very easy. It had to be put together. That was not easy. But for the reader, it's entertaining almost. And so we have all the details here how to transform any local realistic theory into a non-singular, how to transform any non-singular theory to a local realistic one. All right, again, the paper I showed you before with the cartoon, that's the first one to read. It's much easier, but I explained it to you already. That's the real math here. Here there's no fantasy world, it's our world. Again, I'm not claiming that our world is like this. I don't know. What I'm saying is that you should stop claiming that our world is non-local, because there is a complete explanation in terms of local realism for everything that we observe. So forget about having more and more loophole-free experiments. The only way that, as an experimentalist, the only way you could prove that the world is non-local is with an experiment that would disagree with quantum theory. Because when you agree with it, you just add one more stone to the belief that the world is local. That's what you want to do. All right, I'll stop here. Thank you.
Thank you very much. Are there questions?
Yes. So the main argument is kind of similar to the way causality is preserved in quantum teleportation, right?
What?
So the main argument is that they have to meet at some point. They have to communicate. So it's kind of similar to the way causality is preserved in quantum teleportation. And at some point, they have to tell the other one what they observe. So that's where causality is saved. That's where it's local.
It's a bit more complicated.
Okay.
Because in the case of quantum teleportation, you're right that quantum teleportation is not completed before 2 bits of classical information are sent and received. So that's why quantum teleportation cannot be finished faster than light. However, the incorrect but very compelling reasoning is that, fine, you need 2 bits to finish quantum teleportation. But when you're finished, you have transferred a continuous variable. How could you possibly transfer a continuous variable by sending only 2 classical bits? That's why teleportation is so surprising. So you have to explain how this is done local realistically, as Deutsch and Ender did and Charles Bennett explained. But that would take another 2 hours. But it's still, it's a good analogy.
Questions? So I have one. What happens in the game with Alice and Bob and the 2 boxes if the 2 boxes are partially correlated and actually Alice 1 can see Bob 1 and Bob 2? And so, for example, the results may be 1 1 and 1 0. But
Are we talking about the fantasy world or?
yeah, the fantasy world.
In fantasy world, Alice will never see 2 Bobs.
But what if the boxes are programmed differently with some other
Well, you
correlation?
could try to play a different game, I suppose. But the game that is defined in this fantasy world, which indeed you could change and think of all sorts of other interesting variations, but it would not be the same world. In Paul's fantasy world, the 2 Alices will never meet, and Alice will never meet more than 1 Bob. She could meet no Bobs, but she will never meet. She will never meet the 2 Bobs. For instance, if Alice could meet the 2 Bobs, she could serve as a relay for the 2 Bobs to talk between each other, which should not happen. So the 2 Alices are totally independent, and the 2 Bobs as well. And each Alice would only see 1 Bob at most.
Questions? So if not, we can move on to the hall and take the floor.
Thank you.
Thank you very much.